Well, on today's Waste of Time, we're going to talk about batteries and primarily why I dislike drop-in lithium iron phosphate batteries for the most part, especially cheaper ones. And if you are going to go the cheaper route, why it's worth your time to just go ahead and build your own battery. Uh, there's a good 20 reasons why they suck, and you can decide if you like things that suck, or maybe you're into that, maybe you're not into that. I don't know. So the first thing uh, that's a big drawback about most inexpensive lithium iron phosphate batteries are they have a dumb BMS. Don't buy a drop-in lithium iron phosphate battery that doesn't have a smart BMS. It's just a waste of time. When you get it, everything's going to be fine, and things could be fine for years if you have the proper voltages set. The issue is with most dumb BMSs is that you can't see what's going on cell to cell. You can never log into it and see if the pack's getting out of balance. And you don't know generally what type of BMS is in there and what kind of balancing current it has. So you're a little bit in the dark about what your setting should be. And even on the really good batteries, like say, you're going to pay top dollar for a Battleborn battery that doesn't have a smart BMS, you'll notice that they have on their website fairly high voltage settings for float and for bulk. And the reason is they're trying to keep the battery in balance because you can't log in and see if it's getting out of balance. They want to make sure that you're spending enough time in the upper range of voltages so you don't get the battery out of balance. And if there is a good BMS in there, you can put the battery on a high charge and let it sit there for a long time and recover it if it does get out of balance. But a lot of these drop-in BMSs, drop-in lithium iron phosphate batteries, they got these cheap BMSs in them, very low balancing current, and they only balance at very high voltages. So a lot of people try to set their voltages to things that they've read on the internet that prevents cell aging, like very low float voltages, 3.3, or sometimes I even see people running 3.2 float voltage, and they're only charging them up to 14 volts or something like that. And these things they get out of balance that way. And if they do get out of balance, all of a sudden you're having disconnects at lower voltages before you're actually achieving your absorption voltage. The BMS is disconnecting and taking the system offline before you hit 14.4 or even 14.3. And now what do? The thing's sealed up tight. You have no way to open it up, unless it's destructively, breaking the lid off of it, to get in there and see what's going on with the cell voltages. The cells are more than likely just fine. It just needs to be balanced. But the BMS may be so cheap that, if you go and put it on a charger at 14.3 or 14.4 forever and try to make it, rebalance itself, it may take forever to get that done. It may never happen at all because it's so out of whack and it just takes so much time. So that really, for me, just knocks anything that's not a smart BMS completely off as an option. I just don't like them at all. If you're only talking about $50 to $100 difference on the inexpensive drop-ins between a regular and a Bluetooth BMS. So at least have a clue when things start going wrong a couple years down the road, that you can log in there and see what the individual cell voltages are. And if you have one that allows you to actually change your balancing parameters, you can tailor those balance parameters to how you have your voltages set up on your charge controllers and make everything really work together a lot better. The next point is, even if you have a smart BMS can be pretty dumb as well, especially if you're running the batteries in a 24, 36, 48 volt configuration. You're running them in series. Unless you have something that's higher end, like a Victron, or there's several other higher end brands that have a communication cable where all your balancing comes together outside of the batteries, and they can actually move current from one battery to another and keep all the cells and everything that's in the parallel or series strings in order, then you're really never going to be able to keep the batteries perfect. If you're wiring them up in series, you can get a balancer, like a midpoint balancer, that will actually keep the two batteries balanced. So you got inside the battery, you got your BMS doing its individual cell balancing, and then outside the battery, you have a balancer that keeps the 2 or 3 or 4 batteries that are in series, keeps those in balance, because they will definitely 100% come out of balance from each other, just wired up in series. It doesn't matter if you top balance the batteries or whatever, especially if you have it in a high current situation where you're, pushing 100 or a couple hundred amps or whatnot. It's going to happen faster and faster. You put it in a sort of a traction configuration, or you're trying to power a motor with it or something like that, where you're constantly in those higher amp loads, you'll see it happen really quick. So that's pretty much a necessity for any battery that's in that situation, that you're not going to run into trouble within a year or two. And another thing that pops up from time to time is BMS failures. And what do you do when you're probably, you're on a boat, you're not somewhere in the States where you can just easily mail something off and have it warranted or whatever. What are you going to do if you get a nearby lightning strike, the BMS drops out, or it just craps out on its own for some reason? What are you going to do? You pull those batteries out and beat the top off of them and start testing stuff and see if you can replace the BMS with something? I mean, it's just kind of a nightmare when they actually do go wrong. So having built your own battery and having an external BMS that's mounted on the wall that you can bypass if necessary at any time makes a whole lot more sense. And on a boat, I mean, reliability is key. You've got a battery technology that'll last you 10 years, but you've got it in a sort of situation where it's, in my opinion, not going to last 10 years. If you just throw it in there, you throw a bunch of them in parallel or in series and throw them in there and set the voltages the way that they're supposed to be, I still see lots of BMS failures, and even on name brand batteries, still see things getting out of balance over time that have basic, dumb BMSs on them, don't have a lot of balancing current. So it's pretty disappointing to have, a battery chemistry that's super stable and resilient and has so much cycle life in it, but it's stuck in a box that makes it sort of unreliable. I just don't see many of these batteries lasting a decade. I see too many problems already in the. I've only been using drop-ins because I've built most of my batteries the last decade. Only in the ones that I've installed in the last 3 years, I've seen enough failure rate just within the ones that I've installed or other people have had installed that I've serviced for it to become really unappealing to me, especially if it doesn't have a smart BMS in it, and you're just stuck. Do I know what's going on? Well, I don't know what's going on, so I gotta bust the lid apart and get in there and figure out what's going on. And that's just something you don't have to deal with when you have a DIY battery. So let's talk about the benefits of building your own battery. There's really only one downside, is it's a tiny bit of extra money and takes a little extra time. It really doesn't cost that much more money, if any. Say if you're building a 4,000 amp hour, say 400 amp hour up battery, because you just have to buy one BMS for an infinite range. If you buy a contactor based BMS system that's going to be mounted externally, you can have as many cells you want wired in a parallel series configuration on that BMS. You just got the one upfront cost of a really nice BMS, like say an REC BMS that's compatible with pretty much anything you'd want it to be compatible with. Super rigid, reliable system. You're going to be $400 into that. So if you're replacing 4 drop-ins, even if they were cheap drop-ins that you're paying $300, $350 for, maybe less, the cost of the cells combined with the BMS, if you're doing at least, you're replacing what would have been 4 drop-in batteries or 2 larger drop-in batteries, you're about break even there. And one of the things that really increases the reliability is not only do you have one BMS that's externally mounted that you can, at any point, you're going to be able to open the lid of your battery and test the cells if something's going wrong, or bypass your BMS in an emergency situation that you've had some sort of electrical fault, a nearby lightning strike or something, to get everything back online. Just the inherent design of your cells being in parallel, then in series, rather than what's going on when you have multiple drop-ins, which is everything's wired in series and then it's parallel together. So there's no way to move the current from individual cells in each pack back and forth unless you have a really expensive battery that has a communications cable and external balancing like a Victron battery or something like that. So you can have as many cells as you want in parallel before they're series, and they're all going to always be the same voltage, and then your balancer is going to balance in between that 4, 8, 12, however many, to whatever voltage you're wanting to do, is going to take care of that. So you're not going to have issues with the battery coming out of balance ever, really. I mean, unless your BMS has a failure or something like that, that's just not going to be an issue. Something, you can power up, set the voltage settings the way you want, and you're not going to have to mess with it for a decade. And being able to run the voltages you want to run on the battery when you build your own pack there's a pretty decent sized benefit to being able to configure your BMS to the voltages that you want to run on your charge controllers for better longevity of the cells. If you want to run that really low float voltage, you don't want to have to get up into the higher end. You don't want to truly charge the battery to 100%. You want to charge it to 95%. You want to charge it to 14.1, 14.2 rather than 14.4, 14.5. Then you can do that, because you'll know exactly what absorption settings you're wanting to use, what float settings you're wanting to use to achieve that. So you can go into your BMS and you can tailor your balancing window in order to to make that all work together, so you're always getting good balancing. And if you're using a quality BMS, you're going to have more balancing current. So even if there is a smaller window there from the way that you've set the battery up, it'll move more current because of a proper 1 amp, 2 amp or more active balancer inside the BMS. So if something does start to go wrong, you'll know. But if you set it up properly, for the settings and parameters on your charge controllers, then you shouldn't have an issue at all. And another advantage to having these external BMSs, like say an REC, or there's several others. What I really like about the REC, it's a little bit pricey. It's a contactor-based BMS rather than a MOSFET-based BMS. So you don't really have any current limits. Basically, the box just does what it does. It controls larger contactors that turn on and off your discharge and charge circuits. Normally those are all inside the BMS, driven by MOSFETs that turn off and on. And those things, that's something extra to fail. A contactor can fail too, but if you use a proper contactor, it's extremely unlikely to fail. But there's so many other things that can fail, and there's so much heat wasted whenever you start moving hundreds of amps, through a transistor-based, a MOSFET-based BMS. All these additional parts and heat loss and heat in the BMS that's constantly there just makes the system way less reliable and less efficient. And those controllers, like say an REC, or even if you're doing lower amperage and you want to run a JK outside of the case, you've got different inputs and outputs and much more configurability to directly work with things like Victron stuff, Victron ecosystem, wake speed, alternator controllers, all the CAN bus stuff that you can actually go in there and configure it. And not that it just has CAN or RS-485 or whatever protocols. There's plenty of inexpensive BMSs that have that. But better BMSs built for this task have configurability beyond just having that protocol. You can actually go in there and configure the settings inside those protocols, so you can get it to do whatever you need to do with equipment that you may change out later on. You might be upgrading your inverter or your battery information system, and wanting everything to jive together. And that's just something that it's already going to be in place. You just got to go back in there and configure it to work with whatever you need it to work with. Another thing is the configurability. On a boat, you only have a certain compartment size, or you only have a certain amount of square footage that you want to use up. And being able to shape the battery and build it out in the way that fits your compartment perfectly makes a lot of sense. Most people, you have a compartment that was built for some drop-ins, so you just kind of work with what's on the market to use that space effectively, and you go that route. But you're not taking advantage of the space that you have very well. You can get just about double the amount of density in the same square footage than you can with most drop-ins. There are some compact drop-ins that don't waste a lot of internal space, but even those, you can get a lot more density than you can with a drop-in building your own pack. Even if you have 3/4 inch walls in between all the cells and a space that you can get about 900 amp hours at 12 volts, you're basically just replacing what 4 Group 24 batteries would take up, or 4 of your average LiFePO drop-ins. You know, that would have got you 400 amp hours. You can get 900 amp hours in that same area, and you can make it tailor it to fit that area perfectly, not, you know, have to have all the tie downs and strap downs and, you know, making it work. And another thing that I really dislike about drop-ins, especially inexpensive drop-ins, is the construction. The construction is usually not great. They don't even, in most of them, stabilize the cells. They aren't physically constrained. There's a lot of foam blocks and taping and all this sort of stuff. And even if they have nice connections and bus bars on them, you still see a lot of things where there's no internal structure inside the box. There's just padding or something like that, yeah, it can get knocked around. Nothing's going to get hurt. But the cells actually being physically constrained increases their lifespan, and it makes them vent properly. They don't swell out the side because you don't have them constrained. You know, they don't push the sides out, and then later on maybe the venting will happen if there was an emergency, you know, situation. And also, you know, when they swell up from the sides, you can put tension on the terminals and you can short the terminals out. You know, even if you have welded terminals, you know, you get a really bad undercharge. The BMS goes bad. The battery gets undercharged. You charge it back up. The cells swell up. You don't see it on the outside of the case because there's all that extra room in there and they're not physically constrained. So the batteries start prying against each other like that. And, you know, you can either break the terminal loose from the top of the prismatic cell, or you could potentially, you know, push far enough that something shorts together, and I don't even want to think about that. I haven't seen that happen, but I've taken apart a bunch of drop-ins where that almost happened. Like, it was just on the edge. Like, things inside the box had actually broken loose and almost fallen down on the terminals. You know, the thing is just, it's just swollen out like this and it's still not touching the side of the box. It's just a poor design. If the box was built specifically for the cells, you know, they should slide down in an enclosure that can keep enough tension on them that if they do end up swelling, that they'll be constrained and they'll vent, not just expand out and potentially cause a dangerous situation. And there's really not that much expertise needed to build your own battery. It's I mean, a few hours of watching YouTube videos of people doing it, and I mean, there's a group of cells in parallel, and then they're wired in series, and then they go to a BMS. I mean, there's just not that much going on there. What you do need, you know, the basics of, you know, having all the terminals clean, having everything sized properly, using properly gauged bus bars and everything, so you get the right materials up front. But assembling the thing or building an enclosure for it, you know, not everybody's a carpenter, but one of the materials I like to use is HDPE or Starboard 3/4 inch, and to make a really nice enclosure for your box that's not going to allow any cell swelling. It's, you know, it's rigid enough, but something that's not going to wear like wood or corrode like metal. It's just a really nice material, and all you need is a circle saw and a router, or like a little $30 router off of Amazon, and you can make a really nice looking enclosure. So it's not that big of a deal. You know, most of those tools, if you don't have them, you can borrow them for a day. Somebody will let you do it. And it's very easy to set the cells up on the base plate and just cut your dividing walls throughout the end and put your end caps on. You know, put some clamps on it, put a little bit of tension after you put all your isolators in between the cells, and then just screw the box down around it slowly, and then build your lid, and then you can just route it from the outside. And it's something that even a novice that's, you know, barely worked with wood that much can pull off in an afternoon easily. So I guess that's about it. I've crapped on drop-ins for, you know, long enough, and I know there's plenty of you out there that are gonna be like, I've had my drop-ins for, you know, 4 years and I've never had to touch them and they work perfectly. You know, this isn't true. you can be one of the lucky ones and you had it set up right initially, you did your wiring right, and even if you don't have a smart BMS, you know, you can be one of the people that didn't run into issues. But trust me, the issues are out there. Talk to enough people now that there's so many drop-ins and they're so cheap on the market, and they've been that way for 2-3 years now. Uh, you know, talk to people and say, what happened? Oh yeah, you'll start hearing stories of, oh yeah, it worked. I didn't really have any trouble. It worked great for years, and then all of a sudden it started disconnecting, and then I had to get somebody else involved, or I tried to warranty one, and it was turning off, and you start hearing this stuff more and more as the years go by, and this is something that you're usually having to change parts of your system or upgrade parts of your solar charge controllers, and reconfigure things. You're making an investment. You want that investment to last 10 years. There's no reason to put all that time and money and thought and inconvenience of shipping things into something that's not going to be reliable for a decade. It just doesn't make any sense to me. So I know it's building your own battery may seem intimidating for some people, but if you're even remotely handy, if you have a basic understanding of electronics, I would say go for it. Even if once you're done, you have to have somebody to make you feel comfortable. You want somebody to come by and lean over your shoulder for an hour, and you have to pay them $50 or something like that to do it. I mean, it's still worth it. Now you have a completely you have full working knowledge of how your battery works, how things are disconnected, and if something goes wrong, well, what do you have to do? You unscrew the top of the battery off, check each cell with a voltmeter. Okay, they're all good. The BMS is off for some reason. It crapped out. Okay, we'll bypass it for now, or we'll get another BMS on the way. And you're just going to have a working knowledge of the whole system, rather than there's drop-ins at different voltages, and whenever you log into their app, they all say they're at different charge states, and you're thinking about all these additional layers of things that are really unnecessary. So I guess that's enough of me crapping on drop-ins. They're a necessity in many ways, and we're going to see them for a long time. But I think there's still a little ways to go before they are quite what people think they are now, where they get to the reliability and durability of a high-end battery or a DIY battery. So if you're on the fence about going one way or the other, I would highly recommend that you go with building your own battery.